Today we want to look at this region again. We've written a triple integral in rectangular coordinates for this circular paraboloid, also in cylindrical coordinates, and today we want to look at spherical coordinates. So for rectangular and in this case, for rectangular and the cylindrical coordinates, we've been able to just say what's x between, what's y between, what's z between, and then what's r between, what's theta go between, and what's z between. We just had to update our, make sure that we update our dv to include the factor of r that turns d theta into a length. So today we want to write a triple integral for this solid, this circular paraboloid, in spherical coordinates. One of the things that is going to be tricky about this one is the fact that the top is flat, and spherical coordinates are less good at describing things that are all flat. So let's see how that will go. All right, so let's remind ourselves about how rectangular, cylindrical, and spherical coordinates are related. We scroll down to this top view and kind of this three-quarter view just of the coordinates. What we want to do is see how x, y, and r and theta and rho and p and z are all related. We have to know how all these different coordinates are related. Some of them are the same. The z in rectangular coordinates is the same as the z in cylindrical coordinates. The theta in cylindrical coordinates is the same as the theta in spherical coordinates. Let's drop this back down to the plane and remind ourselves of the relationships between r and theta and x and y. Down in the xy plane, we know we've got two sets of relationships. We know that r is the square root of x squared plus y squared from the Pythagorean theorem. And if we notice that this y is also opposite the theta, we could say theta is the tangent inverse of opposite over adjacent. So here's a relationship between r, x, and y, and r and theta and x and y. The easier one to remember here is solving for x and y, because x and y are the horizontal and vertical components of r. So we could write x, we say x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. So it's thinking of r as a vector and writing the components, horizontal and vertical components of r. As far as the relationship between rectangular and cylindrical coordinates, this is all we need because the z is the same in both rectangular and cylindrical. It puts the same third coordinate on top of polar coordinates and rectangular coordinates. The weirdness happens when we start switching to spherical coordinates. One of the pieces that we needed for spherical coordinates is how r is related to rho and phi. To get at that, just like when we needed to turn dv into, d phi into a length and d theta into a length for the volume in a spherical coordinates triple integral, we cared about this distance here, this side opposite the phi. So this red line, this red segment is the same as the green segment below it. So that is R. We can also see a right triangle here. And this red leg is opposite of phi and equal to R. So that gives us a relationship between our cylindrical coordinates and our spherical coordinates. We can see that R is going to be rho times the sine of phi. So R up here is equal to rho times the sine of phi. The theta in cylindrical coordinates is the same as the theta in spherical coordinates. The other thing that we'll need to get is how z is related to rho and phi. Now notice in that triangle where r is rho sine phi, the side adjacent to phi is the z coordinate. It is sitting on the z axis. So z is going to equal rho times the cosine of phi. So we're breaking rho into components, rho sine phi and rho cosine phi. Rho sine phi because the r is opposite phi and z is adjacent to phi. Now we've established a relationship between r and r rho and phi and z rho and phi. Any questions? Now, if we just start mixing and matching, we can write x in terms of rho, theta, and phi. So we know that x is equal to r cosine phi, and r is equal to rho sine of phi. So I could write x as r rho sine phi times cosine of theta. And we could say that y is r sine theta, rho times the sine of phi times the sine of theta. So now I can take rho, theta, and phi and calculate x and y coordinates. So just take your rho sine phi . Then on top of this, we can have z is equal to rho cosine of phi. That's the same z that we have in cylindrical coordinates. So we just need to copy it over to our rectangular coordinates. How's everybody think? So how are we going to represent that flat top where z is constant? In rectangular and cylindrical coordinates, z is just that vertical distance from the origin to the point, or from the xy plane up to the point. So if I want a flat value for z, I just pick whatever constant I'm using. I think it was 9 in this case. To get the flat top in spherical coordinates, we just have to take z and make it constant. So flat top in spherical coordinates, we're just going to start with z equals constant and then replace z with rho cosine phi. Oops. So if I want to solve for rho, I could solve for rho. And that'll tell me that rho is z divided by the cosine of phi. Or if you happen to look this up, that's why I would say z secant phi. So one way we can describe that flat top is with a rho equal to z times the secant of phi. Any questions? Let's think about the values of rho. Z is constant. Let's think about the values of rho for different values of phi. When phi is equal to 0, we're talking about a point on the z-axis. So I want to think about different values of phi. When phi is equal to 0, then we're dividing by the cosine of 0, which, sorry, 0. Phi is 0, cosine is 0. When phi is equal to 0, the cosine of 0 is equal to 1. And so the secant of 0 is also equal to 1. So cosine phi starts off at 1, and so secant of phi is also 1. Then what we want to do is think about what happens as phi increases. Phi equals 0. Phi equals 0 is directly above the origin. Then as phi increases, we drop this angle down towards the xy plane. So if we just increase phi to, let's say, pi over 4, cosine of pi over 4 is root 2 over 2. And so secant of pi over 4 is 2 over root 2. And let's see what's happening. What's 2 divided by root 2? So 2 divided by root 2 is just the square root of 2, which is 1.414. We see our rho has increased. So we start with a secant equal to 1. And then as we move theta to pi over 4, the rho had to increase. We're at a point further away from the z-axis. If this distance is 1, then when phi is 45 degrees, this distance from the origin to the point is square root of 2, 1.414. If we increase phi a little bit more, pi over 3, 60 degrees. Cosine of 60 is a half. So the secant of 60 is 2. Notice that as phi increases, rho has to increase as well. As phi increases, rho has to increase as well. Now, the interesting thing happens when we get to phi equals 90 degrees. Once phi gets to 90 degrees, that means phi is sitting, going all the way down to the xy plane. So if we try to have phi of pi over 2, the cosine of pi over 2 is equal to 0. And so the secant of pi over 2 is undefined. But more specifically, it's undefined and approaching infinity as phi approaches pi over 2 from the left. So specifically, it's undefined. But what's happening is we are approaching infinity. So if I want to touch the ceiling, when I'm standing directly below the ceiling, my arm just needs to reach the ceiling. As I lower my hand, my arm needs to get longer to reach the ceiling. This works all the way down until my hand is almost parallel with the floor. And so when my arm is parallel with the floor, my arm has to be infinitely long to reach the ceiling. Clearly, something's going to break, right? I'm going to have to cheat and point up a little bit. But remember, with phi is measured by pointing straight up at 0, and it drops down, and that's how we measure phi. So phi equals pi over 2 is horizontal, it's parallel to the xy plane. So if I'm pointing parallel to the xy plane, z equals constant is infinitely far away. We can't get there. And we can see that happening. We can see the secant. We can see the secant multiplier going from 1, pointing straight up, to root 2, to 2, and then it just keeps on increasing to infinity. Any questions? Everybody okay? So when we go to set up a triple integral in spherical coordinates, these are the things that we have to think about. What is rho going to go between? What is theta going to go between? And what is phi going to go between? Any questions? Comments? Deepa? Any questions about setting up triple integrals? One question might be, how do we write the spherical coordinates for this solid? I think I told you we would do this today, but I'm still stalling. If I just tell you I'm going to do it, if I just tell you when it's going to happen, you'll just wait for it to happen and not work on it. What happens if you ignore this problem for the rest of the semester, final exam rolls around, and this is the one problem on it? That would be pretty hardcore. I would not do that on a final exam. But then again, I think final exams are kind of BS. Let's think about some more parts. Let's think about some more parts, more things that we could think about with this particular picture. Actually, no, I want to leave this as is. I will draw one more view for you. If we think about the side view, the other pieces that we'll want to think about is from the side view, we're looking at z equals x squared plus y squared. And so we also wrote this as z equals r squared. We have expressions for x and y in terms of rho, theta, and phi. We also have expressions for r in terms of rho and phi. So the other hint I want to drop on this one. Remember when we're thinking about what rho is between. Rho starts up at the origin and goes to the end, and goes to the boundary of the solid. So one of the things that's going to be tricky about the triple integral for this particular solid in spherical coordinates is that let's think about what happens. Let's draw some distances from the origin to the boundary of our solid. So we could start off with phi equals 0. That'll set a rho up to just along the z-axis. But then as phi starts to increase, rho is the distance from the origin to that boundary. But then something happens. This boundary hits a corner that we can see from the origin. So once phi once our rho is pointing at the corner of our solid, the end changes from the flat top to the paraboloid side. And now the distance between the two, the endpoints are different. We're still starting at the origin, but instead of ending at that flat top, we're ending along the parabola. So that's one of the complications. Rho starts off looking at the flat top, but at a certain value of p, switches over to the parabola. This makes spherical coordinates very inconvenient for describing this solid, which just means we have more reason to write the triple integral in spherical coordinates, because it's going to help us understand what the integrals are meant to represent. We're going to need two integrals for this one, because during as phi goes from 0 to towards pi over 2, the definition of rho changes. We start off measuring the rho from the origin to the flat top. That's no problem. We can just use a secant, but at a certain value of phi, we hit that corner, and rho starts off at the origin and goes towards the paraboloid. Any questions? Comments? Deep thoughts? How's everybody okay? Everybody looks so happy to be here. Y'all look like this. Is it just too easy? It's too easy, isn't it? Multivariable calculus. It's just like single variable calculus. All right. So this is, we just want to continue working on this DVD bonus material problem. I want to start off yesterday with 0 instruction. Today, I wanted to add a few extra instructions, converting about how you can think about converting from one set of coordinates to the other and what those expressions mean. And I wanted to point out one of the difficult things that happens in this particular integral. The other thing that we're going to want to do is learn how to type with the equation editor so that when this problem shows up as a graded discussion or quiz, I've decided how I'm going to categorize it. You can type in your triple integral. This will be described with as find the volume, or write a triple integral for the volume. So we'll need to know how to do integrals. If you want to write a definite integral in the equation editor, if you press the integral button and then do a subscript and then A and then a superscript for B, that will give you an integral from A to B in the equation editor. So the integral symbol is just a button that you can press in the equation editor. If you do a subscript A, that'll put a lower bound of A. Then a superscript of B, that'll put an upper bound of B. Then you can switch to advanced and see how to type that. Without the interface. All right, that's going to do it for today. Work out how to describe this solid in spherical coordinates. That's going to do it for today. I'll see you all on tomorrow. Have a good day, and thanks for playing.